And now we will start our next part. This will be tutorial by Pavel Sherstnev. Tutorial is titled Thefittest Library, Evolutionary Algorithms and Automation of Machine Learning Models Design in Python. Pavel, yes, we see your presentation, so you may start it right now.
Good day, respected colleagues. Could you please confirm if you see the presentation, if you can hear me?
Everything is okay.
Okay, all right, then I start. My name is Pavel, and I'm a final year PhD student. Today I will introduce the Thefittest library and provide a technical tutorial on its usage. This library is a robust solution for solving optimization and machine learning problems with evolutionary algorithms. It simplifies the application of advanced methods, offering an accessible framework for solving complex problems in real-world scenarios. Evolutionary algorithms have proven to be a powerful tool for solving a wide range of problems. Their strength lies in the ability to find solutions in cases their traditional methods are either ineffective or inapplicable. For example, when the search space for optimal solution involves large or highly complex parameter spaces, or when system information is available. Classical evolutionary algorithms, like the standard genetic algorithm or basic differential evolution, are widely available in popular libraries. However, modern adaptive methods, which can greatly improve performance, are often harder to find. Implementing these methods usually requires a solid understanding of the theory, a lot of time, and hard programming skills. Many libraries are also difficult to set up and use, making them harder to apply in real-world projects. This highlights the need for tools that are simple, accessible, and designed to support modern adaptive algorithms. The Thefittest library aims to overcome these limitations by offering easy access to modern algorithms that automatically adapt to the problem, high performance through JIT compilation technologies, and integration with popular tools simplifies the inclusions of these algorithms into existing workflows, particularly in machine learning applications. Working with the Thefittest library is extremely straightforward. You need only to define the fitness function, configure the algorithm parameters, and start the optimization problems. There is no need to dive into complex implementation details or worry about additional dependencies. Thanks to its versatility and easy of use, the Thefittest is suitable for both researchers and practitioners who wants to focus on solving problems rather than on programming. Before exploring its practical applications, let's take a closer look at what sets the library apart from other solutions. Among the tools in developing the Thefittest, several play a key role in ensuring its quality and usability. First, MyPy serves as a static type checker, helping to catch errors and maintain clear data structures. Second, PyTest is used for automated testing, ensuring the library stability and reliability. And finally, following PIP8 ensures the code is readable and consistent, making collaboration among developers much smoother. The library has minimal dependencies, which simplifies its use and integration. Its core computation rely on MyPy, a powerful library for working with multidimensional arrays and performing mathematical operation, which is central to most of the Thefittest functionality. To boost performance, Number, a modern JIT compiler, accelerates crucial tasks such as executing genetic operators and calculating neural networks outputs. And additionally, SciPy is used for linear algebra tasks. And finally, thanks to its capability with scikit-learn, the Thefittest method can be seamlessly used alongside tools from this popular machine learning library, enabling smooth integration into existing pipelines and contributing combining its algorithms with established data analysis methods. The Thefittest library is divided into 6 modules. Each serves a specific purpose. Let's explore how they interact and what they offer. We begin with the base module, which handles foundational elements such binary trees or neural networks. Next is the benchmark model, a testing tool that provides standard optimization problems as well as widely used data sets for classification or regression problems. Following that are the classifiers and regressor models, which offer ready-to-use solutions for classification and regression problem respectively. The optimization model is the core of the library where the main optimization algorithms are implemented. This includes both classical approaches and adaptive methods. These algorithms can be applied to solve standard optimization problems or to design machine learning models. And finally, the utils model acts as a support toolkit. It contains operators for crossover, mutation, and selection, methods for generating random data, as well as a function for scaling and normalization data and calculating metrics. This model simplifies and automates many aspects of working with evolutionary algorithms. Let's take a look at similar solutions that also provide tools for working with evolutionary algorithms. Deep offers a flexible toolkit that allows researchers to build their own evolutionary algorithms. This library is particularly useful when full control over the process is required. However, it demands significant time to learn and configure, which might not be ideal for less experienced users. SciPy, well known for its extensive scientific computing tools, also includes basic optimization methods like differential evolution. However, it does not provide a modified or adaptive version of this algorithm. PyGat, on the hand, focus on simplicity and easy of use. It's centered exclusively on genetic algorithm, offering limited functionality, but making up for its accessibility. It's well suited for beginners and quick prototyping. Through it lacks support for other evolutionary methods. PyMO specialized on multi-objective optimization, making it useful for tasks that involve balancing multiple goals at the same time. And GPLearn focused on genetic programming and is used for solving regression and classification problems. It's offer a simple and user-friendly interface, making it accessible for many users. However, its functionality is limited to a single implementation of a genetic algorithm and lacks diversity in genetic operators. Okay, when creating the Thefittest, the goal was to take best features of similar tools and avoid their weaknesses. It's worth mentioning that methods like shade, while still effective, are not newest anymore, as many other technologies has been developed. That said, many libraries doesn't even include methods like shade. In the Thefittest, newer and more advanced methods will be added step by step, starting with simpler ones like just differential evolution, and gradually moving to the latest approaches. Performance is one of the key factor when choosing tools for evolutionary algorithms. To evaluate these algorithms from different libraries were tested on the same problem under the same conditions, with the only difference being their implementations. The figures show some of the best results thanks to the optimization using the number library. That said, the main focus during the development of the Thefittest was of making the library easy of use and acceptable rather than just maximizing performance. Since Python is an interpreted language, it's not possible to match the speed of low-level languages. However, crucial operators were optimized to ensure the performance is high enough to handle most task efficiency. Okay, now let's divide into practical use of cases of the Thefittest library. All examples will be presented in the code format executed in Google Colab. Before exploring the cases, it's necessary to install the library. Since the Thefittest is already indexed in PyP, it can be installed using the simple command pip install the Thefittest. All necessary dependencies are installed automatically. Let's start with one classic one max problem, which is widely used for testing optimization algorithms. The goal of the problem is to maximize the sum of bits in a binary string. First, we define the fitness function for the one max problem. This function computes the sum of ones in each binary string of the population. The results are stored in an array and returned as output. To solve this problem, we will use the genetic algorithm class from the optimizers model of the Thefittest library. And main parameters of the genetic algorithms follows number of generations, population size, the length of the binary string, and the selection method. In this case, it was proportional selection. Algorithm is configured by simply passing the previously mentioned parameters at the fitness function. This creates an instance of the genetic algorithm class. Additionally, the frequency of optimizing progress updates using the show progress each parameter is passed. And next, we just initialize the optimization process using the fit method, which allows the algorithm to iteratively update the population and improve the solution. Upon the completion, the algorithm retrieves the best fit individual binary string and his fitness score. This example was pretty simple, so let's explore more interesting applications. Genetic algorithms are not only suitable for working with binary strings, but can also be with binary problems, but can also be effectively applied to real valued optimization problems. For this, it's crucial to define an appropriate method for encoding real numbers into binary representation. In this example, we will solve the optimization problem of the restriction function using the genetic algorithm. Using the self-configuring genetic algorithm from model optimizers. We also import gray code class from the Thefittest library. This class handles the encoding of real valued numbers into binary representation using gray code. We initialize it using the fit method, providing the following parameters: the number of the lower bounds of the variable, the upper bounds of the variable, and the number of variables, and the precision which determines the step size between possible variables. If we need to define different values for each variable, we could pass an array of parameters instead of single numbers. We also import the transtrigger function from benchmark model. And yes, import class self-configuration GA to create model object. We pass all parameters for to self-configuration GA. Fitness function, genotype to phenotype parameter is the gray code transformation, number of iterations, population size, string len, the switch for minimization process, and the switch for keeping statistic of optimization. The fit method runs the genetic algorithm to perform the optimization. On the screen, you can see a 3D visualization. The restriction function used as a benchmark for this case. It's a surface with multiple local optima, presents a challenging, classical challenging optimization problem. Notice the yellow points. They represent the current population of individuals which challenge with each generation. Initially, the points are randomly distributed across the surface, and the algorithm begins its search. As the algorithm progress, you can observe the points gradually shifting towards regions with lower fitness values, reflecting the process of finding global minimum. Okay, let's move to the next case. For real value optimization problems, classical genetic algorithms often fall short compared to more specified approaches, such as differential evolution. One such method, shade success history-based adaptive differential evolution, demonstrates high efficiency in solving complex global optimization problems. In this example, we solve another classic problem of the green-wang function, which involves 100 variables representing a high-dimensional optimization task. We begin by import the green-wang function and shade the algorithm from the Thefittest library. The shade optimizer is configured with the following parameters: the objective function for minimization, the number of variables in the problem, number of generations, population size, bounds for the variables, frequency for progress updates, specification that is a minimization task. Optimization problem is initiated using the fit method, and shade will iteratively search for solution. After completing the optimization, we can also retrieve the best individual and the corresponding fitness function value used the getFittest method. Okay, now let's look at the example of a custom function defined by user. This function we aim to minimize, as shown here, is a spherical function shift from the region. To create the custom fitness function is the Thefittest. It's important to follow the specific format. In this library, genetic algorithm and other optimization algorithms pass the population to the fitness function. The population is represented as NumPy matrix, where each row corresponds to an individual, and the columns represent the values of the variables. This specific structure ensures capability with the fittest optimization algorithms. And the fitness function shows the population as NumPy array. Each individual is represented as a row in the array. For each individual, the results for each individual, the fitness function computes the value of the objective function using the individual's coordinates, as you can see here. And after evaluating, the results are returned as an NumPy array. There, each element is the fittest value for the corresponding individual. As you can see, this a fitness function written in this way is passed to the optimization algorithm as the fitness function parameter. A part of this, the configuration of the optimization algorithm remains the same as the previous cases. Okay, now let's move to another evolution algorithm available in this library. Previously, we looked at optimization algorithms. There, the solution was encoded in a string. Now let's explore other optimization method that use tree-based encoding. Using the example of symbolic regression, we will demonstrate how empirical data can be modeled with genetic programming methods. The task of symbolic regression involves finding an analytical expression that approximates the given data. In our example, the target function is modified sine function. To make the problem more realistic, we add some noise to the data. This function simulates a real data generation process and serves as a test case for this model. To solve symbolic regression problem, we will use genetic programming regressor from regressor model from Thefittest. This function, this class implements symbolic regression using genetic programming. For optimizing the model, we utilize the self-configuration genetic programming algorithm from optimizer's model. The model initialization includes the following requires parameters: the number of iterations, generations, population size, algorithm optimizer, in this case, self-configuration genetic programming, alternatively, other implementation of genetic programming from this optimizer's model from the Thefittest can be used also. And additional parameters, such frequency for progress updating and history retention. Most of the algorithm parameters can be also customized. For example, you can configure the functional or terminal set or maximum depth of the tree and more others. Training the model and making predictions fully aligned with the scikit-learn interface, making the workflow intuitive and familiar for users. We pass the input data X and the corresponding target values Y for training, followed by making predictions. One of the unique features of symbolic regression is the ability to generate analytical expressions that approximates the given data. Using the getTree method, you can obtain a symbolic representation. GetTree method. You can obtain the symbolic presentation of the best solution in the form of formula. This provides insight into how the model describes the relationships in the data using a compact analytical expression. Now you can see this in our outputs. This image illustrates also two results of modeling. The red line shows how this covered analytical expression approximates the data, and the right plot displays a binary tree representing the structure of the derived expression. This image demonstrates the process of self-configuring during the search for the solution. It shows how the probabilities of applying various genetic operators evolves over time. Okay, let's move to the next case. In the coming example, we will explore another potential application of the Thefittest. We continue exploring the capabilities of this library, diving deeper into its application for training machine learning models. In this example, I tackle a classification task using the breast cancer diagnostic data and train a neural network to solve it. In the first cell, we load data set and split it into training and testing sets. In second cell, we create an object for the neural network model using the MLPA classifier class. We configure the model by following a number of iterations: the population size for genetic optimizer, the neural network structure, which contains two hidden layers with 5 neurons each, and the weight optimizer with his parameters. Next, we build a pipeline consisting of 2 steps: min-max scaler for data normalization and model for training the neural network. The pipeline combines these steps into a single training process. The crucial part of this example is the use of pipeline object from scikit-learn library, which highlights the capability in the Thefittest with the scikit-learn ecosystem. This makes working with the Thefittest intuitive and familiar. The MLPA classifier can be seamlessly integrated into the pipeline, making it straightforward component of the workflow. And we start the training process, and in the final cell, we evaluate the quality of the training model using the test set. Second example, another example demonstrates the application of automated neural network design. There above, its structure and the wave are optimized together. This is achieved using genetic programming and genetic algorithms. For this purpose, the genetic programming neural net classifier from the Thefittest library is used. And this class allows searching the optimal neural network architecture, number of layers, number of neurons, their connections, and other with the help of self-configuration GP method or other genetic programming method. At the same time, the network weights are optimized using any evolutionary algorithm method with string representation. In this case, success history-based adaptive genetic algorithm method. One of the key of this approach is the ability to easily replace the default optimizers, as I said, with other available in the Thefittest, making the model configuration flexible and adaptive. After training the pipeline. Standard metrics such configuring metrics and F1 score are used to evaluate the model's performance. Additionally, we can visualize the structure of the obtained neural network using the plot method, which provides a clear graphical representation of the neural network's architecture. All right, let's move forward to the next case. The capability of the Thefittest library with the scikit-learn ecosystem is not provides it's not only provides a familiar interface for working with machine learning models, but also opens up extensive possibilities for integration. In this example, we demonstrate how the capabilities of both libraries can be combined to create effective model ensembles using evolutionary algorithms. We will use standard models from scikit-learn, including linear regression, random forest, gradient boosting, support vector machines, and k-nearest neighbors. These models act as the individuals of the ensemble, providing prediction for the meta model. Now, here the staking regressor class from scikit-learn is imported, which allows to creation of ensembles of models through staking. For this operation, the following the two components are required. The base models, these are the models whose prediction will be used for further processing, and final models, the meta model that is trained on the predictions of the base models and produce the final predictions. This staking regressor is configuring by passing the base models and the final model, which in this case is the genetic programming regressor from the Thefittest library. Thanks to capability of the Thefittest with scikit-learn, we can seamlessly integrate a model from this library into the staking regressor. In this line, this method of staking has additional advantages, as it can automatically reduce the dimensionality of the ensemble and provide an interpretable model for provide an interpretable provide a planar model. As a result, we obtain a clear formula that explains how the individuals of the ensemble interact. Initially, during the development of the Thefittest, it was assumed that ensemble methods such as staking with genetic programming would need to be implemented within the library itself. However, it later became clear that due to capability of the Thefittest with the scikit-learn ecosystem, such an approach was already possible without additional functionality. This realization expands the possibilities of using the Thefittest in combination with existing tools. This enables the creation of powerful ensembles that combines traditional machine learning methods with evolutionary approach. Additionally, it allows leveraging already developed implementation without the need to be introduce new functionality, thereby saving development time and ensuring seamless integration. Okay. thank you for your attention and for the opportunity to be part of this conference. This concludes my tutorial. If you need, you can access all the materials, includes this presentation, through the QR code provided on this slide.
Thank you very much for your presentation. So we have enough time for discussion and questions, so you're welcome.
Okay, thank you for a great tutorial. I have a question. Have you tried to compare the solutions of problems obtained with your library to other libraries for the same problems? For example, by using some metrics like hypervolume or generational distance, just to understand whether the solutions are better in some ways.
Oh, sorry, but I don't understand the second part of your question. Metrics and methods.
Yeah. Well, I just wondered when I watch the table you've shown, there were some rows where you have classes for your library and for some others. So I thought it maybe a good idea to compare the solutions you get by your methods to the solutions for the same problems obtained by methods from other libraries. So by using some metrics that give us a representation of how good the solution is, maybe comparing to each other.
Do you mean do you mean effectiveness of these methods?
Not effectiveness of the methods, but the characteristic of the solution. Like, how is it? Is it? For example, you get the Pareto front. It can be dense. It can be somewhat sparse. So in comparison, the dense Pareto front is better. Something like this. There are some metrics like hypervolume, generational distance to compare these solutions. So,
no, I'm not yet.
Okay. You haven't tried. Okay.
Not yet compare in this.
Thank you.
Thank you.
Thank you for the question. Does anybody have another one? Okay, let me ask you. Well, if I know many frameworks actually have only some, how to say, API, which means Python only used to start some calculation, but actually all algorithms are implemented using, for example, C++. What was motivation to implement everything using Python? Python not very fast language for calculation.
Okay, thank you for your question. Now, it's just because I started to develop this library just for me during my working with evolutionary algorithms, and it's just convenient to use in Python. And JIT compilation, like number, can provide performance of Python code, and I'm not yet compare with libraries implemented on C languages, but I think it's of course worse, but I think not more worse. If I did short my answer, I just it's because convenient for me, because I'm well Python developer, but not good at C languages.
Okay, I see. And maybe it's not a question, but suggestion. You have shown table when you compare different frameworks. There is well-known framework which contain a lot of evolutionary and other optimization techniques. It also have self-adaptive techniques, island models, parallel computations, and so on. This is PyGMO 2. I haven't seen.
HMO2.
Yes, if you don't know or never meet it before, I can write it in a chat for you not to forget, and you can compare
Okay,
later.
thank you for your suggestion.
Okay, we still have time for discussion. If anybody have question, please ask. Well, my final question. You said that you use some state-of-the-art algorithms which are very good and user only will start them to get solution. But actually all algorithms you use are very old. If you look in some competition in the field of evolutionary computations for last, for example, 3 years,
Mhm.
you will find much better algorithms. And also you can find source codes for all these algorithms. That means that you don't need to implement it how you understand it. You just can take this code and translate it in Python and use the same algorithms, how authors of these algorithms do it.
Yes, you are correct. These are relatively outdated algorithms. However, in science, they build on each other. It's necessary to implement them first before moving forward. Development is
The same
ongoing.
about benchmarks. You use 2005 competition 15 years ago. Uh, as I know, some benchmarks are written in C++, so if you will translate it into Python, it will be very great because many researchers want to try it in Python, but don't have such a possibility.
Yes, I agree with you. I'm thinking about it, but just I'm not yet ready for this.
Well, nevertheless, thank you very much for presentation. I think it's a very good attempt to enhance our tools in solving optimization and machine learning problems. That's why great thanks for you for such applications. So we have about 10 minutes for short break, and we will continue with next presenter. This will be keynote speaker. So right now we have a break.